All right, guys, we're starting the lesson in a moment. This is March 26th, of course, and we will be using this live stream thing that we tried for the first time yesterday to actually do the lesson, and it just seems to make more sense for me instead of making a video, editing the video, producing the video, uploading the video, and making sure it gets on Google Classroom when I can just do this one and done kind of thing. So we're going to try this and see how it works. I'm going to be thinking on my feet. But I got a couple camera angles here, so let's see what we got. This is, I'm talking to you. Then I have this thing here where I can write and draw some pictures and get you through. Periodic table there, picture of myself. Awesome. Then, if we ever have to refer to just the periodic table, I could show you that. And if I ever just want to use the entire paper, I can write everything I want here without anything in the way. So that's going to have to be how we do things, at least for now. And I got everything set up. I'm hoping that the microphone sounds pretty good too, because I have figured out that I actually had it hooked up wrong yesterday. So let me know what you think of the audio quality compared to yesterday's live stream, because this is a little bit different of a setup. And let's see, the periodic table, is that cut off? If I switch to this, is that cut off at all, or can you see the entire periodic table? Is the top of my head cut off? I'm trying to figure this out. So we're going to work together and get this. No, it looks okay. So top of my head is not cut off. Periodic table is not cut off as well. Anyway, back to this thing. Okay, so you guys have a rare opportunity here doing these live streams to actually ask questions on the fly as we go. So if for some reason I'm explaining something and you're not quite sure what I mean, you can ask a question. Now, there is a delay between what I'm saying and when the comments pop up. So you're going to have to work with me on that. And, okay, I'm getting confirmation that the audio is good and nothing is cut off. Thank you, Zach and Matt. Having said all that, if you have a question, get it in there, and I'll do the best I can to get to it as soon as I can. Let's see. Okay. Thanks, Nick. Okay. So if for some reason you're in non-honors chemistry and you've stumbled across this stream, that's fine. Feel free to stay and hang out. But this is only for honors, and that's why I titled the video what I did. So this material is only for honors chemistry. Anything else for non-honors, you guys got to go to that Google Classroom and see what I posted for you there today. All right, so let's start just by going over a very quick review of the electron configuration, because what we're going to be talking about is electron configuration of ions, okay? Earlier in the previous unit, we talked about electron configuration of neutral atoms. Now, this is different because to go from an atom to an ion, we have to take away or add electrons. And depending on what you do, how many you give or take results in a different charge. So if you think back to earlier in this unit, we were discussing things like nitrogen, which we would call a nitride. Now, nitride, if you go back to the periodic table, nitride is in the column all the way to the right, and it's in the -3 column, which means it gains 3 electrons. Okay, it started with a neutral atom, it gains 3, it becomes -3 more times. Oxygen is going to be -2. Fluorine is -1. Now go all the way to the left and look at lithium. Lithium is going to be a +1. That means it lost an electron. Beryllium, which is right next to that, is going to be a +2. It lost 2 electrons. Now let's do the electron configuration of a neutral atom. Let's do something. Let's do oxygen. Okay, oxygen's a good example. So I'm going to go to this. Let's see. Let's switch it to this thing. Let's do the electron configuration for oxygen. Now, one of the complaints that I got, I wouldn't call it a complaint, but more of a constructive criticism, is that the writing on the pencil was very light, and it wasn't that dark enough. So I switched to a pen, and we'll see if this makes a difference. All right, so we are doing the electron configuration for oxygen, and we're doing the neutral atom. So that is 1s2, 2s2, p. Let's bring up the periodic table and we'll count it over. Oxygen is going to be P1, 2, 3, 4. All right? So P4. Okay? All right, now, an oxide, which is an O with a -2 charge, gains 2 electrons. Okay? So I'm going to take 2 more electrons, and I'm going to add them to this configuration. Now, if you think back to what we talked about, the p orbital can hold up to 6. So it's only got 4 to start. I'm going to add 2 more and bring it up to P6. That's really all you're doing. There's some caveats that we'll be going over soon, but for the most part, you're just adding or removing electrons based on its charge. Oxygen's -2, so it gains 2. So I put in there for the P6, okay? Now, having said that, I'm going to slide this down over here. Let's do another one. Let's say we're doing fluorine. Okay, and then we'll do a positive one. Fluorine is 1s2, 2s2, p5. All right, just a couple more spots down on the periodic table from actually just one spot. Well, fluorine is going to be a fluoride with a -1, so it gains 1 electron. 1s2, 2s2, p5 becomes 6. It's that simple, okay? Now, I'm going to explain where this is all coming from shortly, but let's do a couple more. Let's do a positive ion. Let's look at, say, what do you call it? What were we doing? I used lithium and beryllium, right? So let's go back to the periodic table. So we got lithium is going to be 2s1. So let's go back to this thing. Lithium, 1s2, 2s1. Well, lithium is a +1 when it's a charge, so I got to take 1 away. I'm going to take it from the last one I put in there, which was the 2s1. All right, so 1s2, I take 1 away. That empties that s out, so now all I'm left with is the 1s2. Beryllium will be real similar. So if I just scoot over 1 more element there, I get 1s2, 2s2 for neutral beryllium. Beryllium, when it's a charge, is +2. So I'm going to take 2 electrons away. You always take it from the outermost electrons, the ones that are furthest from the nucleus. In this case, it's 2s2. I got to take 2 away, so I just empty out that s, and I'm left with 1s2. Now, what you should be seeing is a slight pattern here. Okay, lithium and beryllium both become 1s2. If I go back to this one, oxygen and fluorine both become 2p6. Now, the reason for that is because what I'm about to say will explain everything as to why it becomes a actual ion. So everything takes on a new charge when it becomes an ion, and the charge that it takes mimics the electron configuration of the nearest noble gas. I'll say that again. The reason why the charges are what they are is because those elements, when they become ions, are trying to be like a noble gas. And it's really easy, for the most part, to be like a noble gas that they're really close to. So that's why fluorine gains 1 to be like, here, let's go here. So that's why fluorine gains 1 to be like neon, because it's just 1 away. Oxygen gains 2 to be like neon, because it's just 2 away. Nitrogen would become a -3 by gaining 3 to be like neon, because it's 3 spots away. Hopefully you're starting to see that. Now let's go down to the next row. Magnesium. Magnesium is in the same column as beryllium, and I told you earlier that beryllium column and everything down is +2. Well, magnesium's +2. The reason why it's +2 because it loses 2 to be like neon. Okay? It always goes back to the nearest noble gas. And it just, once you see this pattern, it only makes sense. Now, what I'm going to do is I'm going to put a couple of ions on the piece of paper. I want you to give it a shot. I have to blow my nose, so you're going to give this a try, and I'm going to take care of that while you do this. So let's go to... let's see. Let's go to this screen here. let's go to this screen. All right. So let's give you an example or a problem to try on your own. I want you to try phosphorus when it's neutral, and then phosphide when it's a -3. So give me the electron configuration for phosphorus there, and then the one for phosphide right there. And then I want you to do, let's say, let's not get crazy here. Let's do sodium. So Na and Na plus 1. All right, try that. Take a minute, give that a shot. And if you guys have any questions, feel free to put it up on the chat as we do this. At the moment, there's 11 people in here, and I haven't really seen too much feedback just yet. When and if you get the answer and you're the first one, leave me a comment saying that somebody got it so I can go back to teaching. This is almost as boring as being in class. I think the biggest problem I'm facing is that there's some sort of delay, of course. So I'll say something, and then I have to wait for you to see it, and then I have to wait for you to actually try it, and then I have to wait for you to actually give me a response. So the sooner the better. And again, if you have any questions, you better leave them there. All right, with that in mind, I'm going to start doing the neutral phosphorus and sodium just to get you started. So I'm going to bring up the periodic table. Phosphorus is all the way over here underneath nitrogen. So it's going to be a 3s something or a 3p something. 1s2, 2s2, p6, 3s2, 3p3. All right, so bring that back up for you. All right, so that's what I got for phosphorus neutral. Now sodium, if I bring back up the periodic table here so I can say it, sodium is actually before that. So 1s2, 2s2, p6, 3s1. Okay. All right, thank you guys for letting me know that you're caught up with me. That's going to be a big help with me kind of steering the ship a little bit. So anyway, those are the electron configurations of the neutral examples that we have, phosphorus and sodium. Now, I don't need anything else in order to continue. I know that phosphide is -3, okay? So I'm going to just take 3 away. And it only makes sense to remove it from the P3. So what I have left is 1s2, 2s2, p6, 3s2. That's going to be the, what do you call it? Actually, no. See, I just screwed it up, didn't I? -3 means it's going to gain 3. So P3 becomes P6. That makes more sense based on what I was saying earlier. All right, next, let's look at sodium. Sodium is a positive 1, so it's going to lose, and it makes sense to just take away from the 3s1. So we got 1s2, 2s2, P6. There we go. Okay, now we're back on track. This makes more sense. All right, is that what you guys got? Hopefully those that are following along that said they're finished, hopefully you got something like that, and hopefully it makes sense, okay? Now you can do the electron configuration for any ion as long as you know the charge. We're going to do a weird one, and then I'll start explaining more in depth what it means to be stable and not stable. This goes pretty deep. So here we go. Let's take a look at now, you know what? Let's start explaining these rules instead. So there are 3 rules that I want to go over. There's 1, 2, and 3. Okay, the 3 rules. Let's just go right to a document. Get rid of my ugly mug there. So we got 3 rules. Okay, first, Cynthia, you got it? Does that happy face mean that you're good? I'll wait for your answer while I keep going. So the first rule is, how can I word this? The reason why these things are gaining and losing electrons is to be more stable. So stability is the name of the game here. These things are unstable when they're neutral, so they're gaining and losing electrons in order to become more stable. So that's the whole reason why we do this in the first place. You got to get these electrons in place to make it stable, or take them away to make it stable. Metals lose to become more stable. Non-metals gain to become more stable. Okay, so here we go. The first rule of being the most stable that you could possibly be is going to be like a noble gas. Be like a noble gas. Okay, that's the first goal. That's the most stable you can be. That's why everything we've done so far, good job, Cynthia. That's why everything we've done so far has been the same configuration as the nearest noble gas to that ion. So, the next best thing is to be completely filled or empty. Completely fill or empty the orbitals. All right, so this is where we start having some judgment calls here. I'm going to change the screens. Let's go to this thing, all right? And we're going to do a couple examples before we come back to that third. So let's look at, let's say, lead, okay? Lead is way down towards the bottom. Where are we here? This is the screen I want. Lead is way down towards the bottom, number 80-something, okay? Number 82, I believe. All right, so let's do the abbreviated form of just lead, and then we'll do the one for lead Pb plus 2, and then we'll do it again for Pb plus 4. Now, these are the two forms that lead can be. Normally it's neutral, but it wants to be more stable, so it has Pb plus 2 as an option. It also has Pb plus 4 as an option. So we can lose 2, or it could lose 4. One of them is going to be better. Okay, so let's take a look at the periodic table again. Do I have one here with me? Hang on a sec. Because I'm trying to look at this little thing on my screen, and it's just not, I'm getting old. So I got my periodic table here. I'll be referring to this. It might be a good idea if you have one as well. I'll try and pop up the one on the screen every once in a while, but we'll see what we can do. So I'm going to do the abbreviated form for just neutral lead, okay? That's going to be, with the brackets, it's going to be xenon, and then I got to do 6s2, okay? Then 5d1, right? 4f14. Then I can go back and finish up the d orbital, make it a 10, and then I go 6p2. Okay, so that's neutral. That's neutral lead. Everything's good. Number of electrons match the number of protons. Now, in order to become plus 2, it's got to lose 2 electrons. And it just makes sense to take them from the 6p2 for a couple of reasons. One, that is the furthest from the nucleus, and it's also the last 2 that we added. So I'm just going to rewrite it without those 2. And there you go. That is the electron configuration for a lead 2 or a Pb plus 2. Now, to go to Pb plus 4, I need to remove another 2 electrons. I hope that makes sense. We took 2 already. I need to take another 2 to get the 4. So here's how you're going to do this. You can do the brackets with the abbreviation. That doesn't change anything. What I'm going to do is take 2 more away, but they have to be from the furthest point from the nucleus, the part that's furthest away. In this case, look back here. It's going to be the 2 in the 6s. The 5 and the 4 orbitals, those guys are closer to the nucleus. So we have to take it from the 6s2. Even though they weren't the last ones added, they're the furthest 2 away. So I'm just going to rewrite it without that. And here we go. That is the electron configuration for Pb plus 4. It's weird looking. Excuse me. Weird looking, but that's what happens after you take 4 away. You have to take the right 4. You can't just take any 4, right? Because if we start taking some away from different places, it's not going to follow these rules. So let's go back to these rules, okay? I'm going to bring this up here for a sec here. So these are the three rules. First rule, you want to be like a noble gas. Well, lead can't be like a noble gas. I can't take all that away to be like xenon. There's a lot going on here. There's 2 plus 10 is 12, another 14. You're looking at 26 and 28. I can't remove 28 electrons. That's a lot of work. But if you look at option number 2 to be stable, completely fill or empty, it's not as good, but it's a second place. So with PB plus 2, all I did was empty what was in the p orbital. Now what's left behind, everything is filled. I hope that makes sense. So I emptied one out, and I left behind everything else, and that was filled. That's why plus 2 is stable. Now look over to plus 4. Plus 4 is also stable because all I did was empty out the next orbital, 6s2, and I left behind everything that was empty. Now, we need to consider what's going on here, all right? If you look at these two options, well, actually there's 3 here, right? PB, PB plus 2, and PB plus 4. The question could be something like, which of these 3 is the most stable? I'm going to say the most stable is going to be PB plus 2. And here's why. PB isn't all that stable. It does exist, but it's not all that stable because it doesn't follow these 2 rules we've talked about. It's not the same configuration as a noble gas, and there's an incompletely filled orbital. There's 2 there. It's not P6, and it's not P0. So to go from PB to PB plus 2, all I do is take 2 away. I empty that out. PB plus 2 is now considered stable. Okay? If PB plus is, let me rephrase. If PB plus 2 is stable, why would I go through the trouble to remove 2 more just to get to something else that's stable as well? All right, Zach is asking a question here. Do you have to, hang on a sec. I'm kind of a dope still. All right, Zach says, do you have to completely fill and empty all orbitals, or is it stable immediately after you fill it, empty one single orbital? Let's see. I'm trying to understand your question, Zach. That's the biggest problem with this thing. Do you have to completely fill and empty all orbitals, or is it stable immediately after you fill it, empty one single orbital? Well, let's go back to this one. All right, I'm going to go back to PB plus 2 to hopefully illustrate this. PB is not stable because of this P is incomplete. If I empty that P out, everything else left behind is filled. So this is stable. You don't have to have every orbital empty as long as you empty out the ones that are only partially filled and leave behind everything else filled. So if everything here is filled, it's stable. Just like here, everything that's here is filled. And this is stable. But the question is, this is probably going to be more stable than that because it takes work and energy to remove every electron. So why would I go through the effort of taking 2 more away just to get to be stable again? I'm going to stay here. So this is probably more stable and more common in the real world. Zach, I hope that answered your question. Let me know in the thing if that makes sense. All right? Let's see. Hey, Luke, what's up? My morning's going okay. Zach, fill or empty? Not fill, my bad. Nick. All right, so I hope that answers your question, Zach. Let me know what you think. I'm going to move on to the next section here. Now, if you're talking about in terms of stability, you got rule number 1, be like a noble gas. That's the best. You got to be like a noble gas. If you can't be like a noble gas, then your next best option is to completely fill by gaining electrons or empty by losing electrons. I'll say it again. If you can't be like a noble gas, get to a P6, your next best option to be stable is to completely fill everything by gaining or completely empty by losing. So nonmetals will fill things. Metals will empty out their orbitals. I hope that makes sense. All right. The next best option Excuse me. And this is option number 3. This is third place in stability. You can get stable this way, but it's not as good as being stable the other 2 ways. Okay? This is if you can get things half filled. Okay? So let's look at a couple examples here. So you got these 3 rules. Be like a noble gas, top. You got to be like that. If you can't, try completely filling or emptying. If you can't do that, if for some reason you can't find enough electrons or you can't give any away for whatever reason, if you can get your orbitals to be half filled, you're good. Okay, those are the 3 rules and the 3 ways of being stable in that order. All right. Let's look at, let's see here. Let's see. Let's look at, sorry, I'm trying to come up with a good example here. Let's look at chlorine, all right? Chlorine, neutral chlorine, okay, versus chlorine minus and chlorine plus 2, all right? So let's look at those 2 examples. Now, you haven't ever seen this before, but with our newfound knowledge, we can see that it's going to be possible. And we'll actually compare the stabilities of these 3, just like what we did with the lead, and hopefully it'll make more sense. Zach, let me know again if I helped you out with that. I'm just waiting for your response. I will come back to you. I want to make sure you're good. Anyway, chlorine, let's do the abbreviation neon. Then we're going to go, that's 3s2. P5. Okay? Now, that makes sense for chlorine or chloride to just gain 1 to be like, what is that? What is that? That was supposed to be a bracket. So, neon, 3s2, P6. So you can see that in this case, chlorine is just like argon. Okay? It's got the same setup, same electron configuration. Everything's good. All right? Next, if chlorine were to... All right, Zach. Zach gave me the thumbs up. Good work. Now, if chlorine were to lose 2 electrons from what it started with, that means it's going to be same abbreviation with neon, 3s2, P3. I took 2 away. Okay? So to be plus 2, chlorine would have to be half filled in the p orbital. So that's your third rule, your third option. So of these 3, we can rank them in stability from most stable to least stable. So chlorine, when it's a chloride, is the most stable. Okay? That is just like noble gas. That's rule 1. All right, remember this thing? So when chlorine's like a noble gas, that's the most stable. So I'm going to put a number 1 here just so we can rank it. That's the most stable. Okay? The next most stable, or second place for stability, would be this one here, because it's got half of its p orbital filled. All right, I hope that makes sense. That will be option number 3. Okay, and then the least stable would be neutral chlorine. All right, because that doesn't satisfy any of those 3 rules. It's not like a noble gas. Nothing is, not everything is completely filled or empty, and not everything is half filled. So I hope you see where that's going and that makes sense. And my computer's bugging out already. All right, so let's do a very strange one. All right, Matt's got a question first. So what's the most stable is the one that takes the least effort to become stable. Correct, Matt, that's a good way to put it. It's kind of like a preferred state. Electrons will come and go based on the needs of the atom. Okay, so if the atom needs to be stable or prefers to be stable, it will give as many away, or it will take on as many as it can to be stable. So again, the most stable is the one that takes the least effort. So if you could be stable by losing 1 electron versus gaining 2, I'd rather just lose 1, because it's the same amount of energy to lose 1 as it is to gain 1. Matt, let me know if that clarifies what you just asked, okay? I know there's a delay, but give me your best thumbs up like Zach did if you're with me. We're going to do a strange one in the meantime, okay, while we're waiting for confirmation from Matt, okay? Let's look at copper. Now, copper can be +1. Here, let's do this thing. I'm going to go right to this. So I got more room. Okay? Excuse me. All right, so copper can be copper +1 or copper +2. Now, where am I getting that info? Thanks, Matt. Good thumbs up. So we have 3 options for copper. Neutral, +1, +2. The +1, +2, I know from that list that I gave you before all this pandemic thing started. So anyway, copper is in the d orbital. I'm going to use the abbreviation. It's argon. Okay. And then I got to do 4s2 and then 3d9. All right. So that's not stable. Okay. It makes sense that if you were to give it 1 electron, you can simply fill up the d orbital. But the problem is copper is a metal. Copper doesn't normally gain. Its tendency is to lose. So to lose 1, this is where things get a little weird. You ready? I'm going to lose 1. I have to take it from the 4s2 because that's furthest away from the nucleus versus the 3d9. All right? So argon, 4s1, 3d9. Now that looks really weird, okay? What happens is a rearrangement. So I took 1 away to make it +1, but couldn't this 1 electron simply find a way to scoot over here? So this would be the incorrect answer. What really happens in the end when you're done is you get 3d10. Think about that for a minute. 4s1, I took 1 away. I didn't do anything with the d orbital just yet. But this 1 electron sees an opportunity to empty out the s orbital and at the same time fill up the d orbital. So this becomes super stable. I hope that makes sense. Okay? Let me know if you have any questions about that specifically. Nick, I see that you're thinking. I'm not quite sure what that, I guess the kids are calling it an emoji. Let me know what that emoji means and what you're thinking there. All right? If you got a question, let me know. Now, let's go back up to copper. I'm going to change it to copper 2. I got to take 1 more away than what I did here. But here's the problem. I got to take them from the s orbital. So let's just take both away. There you go. That's all I did. There's no option for rearrangement because there's nothing else there. There's no other spot for it to go. So, excuse me. Of these 3, which one do you think is the most stable? All right, take a minute. Try and come up with that. I'm going to stall. Okay, so you have 3 options. You should be thinking that copper +1 is the most stable. Then you should be thinking that there is actually a tie in stability between the last 2, but not true. I'm going to make this number 2 and this number 3. And the reason being is that to go from here to here, I had to waste energy to give 2 away. So this is the laziest way to be stable, and this is the most efficient way of being stable. I hope that makes sense. You guys got to ask specific questions. We're coming up on 35 minutes of doing this. So copper is an example of one that will be changing with the rearrangements once everything's all said and done. Once things have either left or joined the atom, then it could go through a final rearrangement. Not very common, but it does happen. Copper is the one example that we'll be doing. Now, if for some reason another example pops up, we could do any polyvalent that we have on that list. So let's do, let's look at, we already did lead. Tin would be the same way, just 1 less orbital. Sorry, I got distracted. There's a truck driving by. Let's look at iron. Iron's a good one to look at, okay? So get a fresh piece of paper here. Go back to this thing. All right, so I got neutral iron. Now, if you think back to that list, iron can be a +2 or a +3. When I get to the +3, I'll move my face out of the way. Right there, I'll move that so we can see the whole thing. So iron is in the d orbital, okay? I'm going to use the abbreviation of argon. It's actually just a few to the left of copper. So I got 4s2, 3d, let's count them, 1, 2, 3, 4, 5, 6, 3d6. All right, so, excuse me. That seems to make sense based on what we talked about. Now, in order to go to iron plus 2, we have the same abbreviation. We got to take 2 away. The only option I can do is take it from the 4s2, and that leaves me with 3d6. All right, cool, whatever. But let's take one more away. What am I doing here? Let's take one more away to make it a plus 3, okay? 3d5. So based on our rules, I have iron, neutral, versus iron plus 2, iron plus 3. I'm going to say that this is the most stable, only because everything is filled or empty or half. So the D can hold 10 electrons. This has got 5. That's half right there. Okay, I got a question about the s orbital. I'll get to that question in one moment. I'll come back to the copper, I promise. Let's finish up this with the iron, and then I'll get that for the copper. I have it around here somewhere. Anyway, iron plus 3 is the most stable because it satisfies it completes those 3 requirements that we talked about. This isn't all that stable, but it's less stable than this because this takes energy to remove those 2 electrons to become like this. So I'm going to make this number 3 and that number 2. All right, that's the kind of thing you're going to have to be thinking about when you're doing this. Now, let's go back to copper. Now, when you say completely ignore the s orbital, you can't really ignore it because it is there. So let's go back. I have copper neutral. Here's the electron configuration, 4s2, 3d9. Okay? To become plus 1, I have to take 1 away. My only option is to take it from the s orbital here. So that becomes 4s1. Okay? Now, copper sees this as an opportunity to take its electrons and move them around. This doesn't always happen. This isn't something that you'll see often, but it does happen it is possible. Unlikely, but possible. So this 1 electron will get forced to join the d orbital, and now we have to rewrite it as the final answer. So it's not that you're ignoring the s orbital here. There's just nothing in it. Just like the p orbital and the f orbital. There's nothing there, so I don't write it. It got emptied out to work for our 3 rules, and it filled this one up to work our 3 rules. Okay? I hope that helped. What we're going to do is I'm going to kind of leave it open for a few moments. I'll stall and tell you what the plan is for the rest of the week. And if you guys have any questions, I'll be sure to answer them before I go. But after a moment or so, if there's no questions, I'll close it out. These are the electron configurations for ions. Now, in your homework, do I have a copy? Jeez, sorry. So I have a copy of the homework here. If you go towards the back, the last page, well, inside the last page, second to last page, it looks like this thing here. Hopefully you can see that. All right, so that is the homework page we're going to be referring to. Let's do a couple, okay? And again, if you have any questions, did that help? I got a thumbs up. That seems to be the universal sign of we're good. Let me know. I think we're good. All right, let's go to this thing. Let's look at the homework, okay? So it says, write the full electron configuration for the following neutral. We can do that. We learned how to do that in a previous unit. So let's go right down here, so we're not wasting too much time, to the part where we're going to do it for the ions. And then you have to decide whether or not it's stable or unstable. So there's a 2-part answer here. You got to tell me what the configuration is, and then you have to tell me stable or unstable. So beryllium plus 1. Beryllium is up at the top next to lithium. So I got 1s. Ooh, let's do a pen. All right. Beryllium is 1s2. And then 2s2. Now, there's an argument there that regular beryllium is pretty stable based on the rules that we talked about. But in order to become +1, I got to take 1 away. So it becomes 1s2, 2s1. Question, is this stable? I would say it is stable because it's half filled. And that is, where's my list here? Yeah. So here are my rules. I'm going to have paper all over this office. Anyway, here are my rules. Be like a noble gas. Beryllium +1 is not like a noble gas. Everything's completely filled or emptied. Not true. I got S1. There is something half filled. Well, that seems to be okay because S can hold 2, and I got just 1 in here. So this seems to be stable. I would call that stable. You're good, okay? Next, if normal beryllium is 2s2 and I want to make it +2, doesn't it just become 1s2? That's the mindset you got to go through. Now, I would also call this stable because everything is filled or empty. This one would actually be more stable than the previous question because this satisfies rule number 2. This one does rule number 3. Rule 2 is better, second place. Okay? So what I want you to do is try the rest of this page, and tomorrow what we'll do is I'll put up an assignment for this stuff here besides the homework. So I'm stumbling here. Let's go back here. Let me regroup. So I want you to focus the rest of your efforts today on this homework packet, on that one sheet, because now we've covered everything in the unit. You should be good. I don't want to give you an actual quiz or test just yet, but I do want to give you an assignment tomorrow in Google Classroom that focuses on this. So it'll be more questions of this electron configuration stuff, just more time to practice. Then we need to start thinking about how we're going to do quizzes and tests for next week, okay? I got a couple days to figure that out. Tomorrow will be review. Monday will be probably the beginning of coming up with the quizzes and tests. We'll figure it out, and I will let you know. But as of right now, we've finished the unit. So we're at that point where I actually got to get a grade for this unit for you, and that's more on me to figure out than you guys. So I'm going to talk to some other teachers and figure out what they're doing and if it makes sense for you guys. But chances are it's going to be an online thing. Are we still turning in the homework packet? No, at this point, there's no really good way of doing that, and I don't want my email flooded with pictures. So instead, you're going to be focusing on using the homework packet as like a study guide that has practice and example questions. So it's not something I need to collect anymore as a grade. It's something for you to use as practice. That might not be possible moving forward into the next unit where I don't have a packet to hand you. I'll figure something out for you. But I haven't really put in too much assignments online because of you having this homework packet as practice. I hope that makes sense. So I don't need it. It's yours to keep, but it's yours to practice with. Okay? All right, having said that, I stalled long enough. I haven't gotten too many questions. We are currently up to 9 people out of 26 in this live stream. I hope this helped. Now, these live streams, I'm going to leave up as videos, just like the old stuff, in the Google Classroom. So you can go back and rewatch these, pause it, fast forward, rewind, whatever you got to do for the duration of this course. They will be up there. Okay? Okay. So again, tomorrow I'll be putting up an assignment. You might not hear from me, but you can always ask questions. Leave them as a comment or an email. I'll get back to you as soon as I can. All right, guys. Thanks for all the attention and the hard work. You guys are really doing well with everything that's going on. Just keep checking in with the attendance and keep trying the assignments and keep watching these videos. All right? That's all I can really ask. All right, guys. Thanks again, and I'll be talking to you again soon.